All right, honor students, Bloss wants an introduction. So, hey guys.
It's Nicole.
All right, that's enough. Here we go. Section 3, mapping the stars. Patterns in the sky is the first section underneath that. And it says constellations are sections of the sky that contain recognizable star patterns. Recognizable star patterns. That has always confused me because to me, I don't see the pattern that other people see. It just drives me crazy. But they insist that the pictures are actually there. And again, we may see one thing and name it a certain thing. The Greeks, the example I gave earlier, the Greeks saw the hunter and named him Orion. The exact same set of stars. The Japanese saw it and they saw a drum. And so that's what they named it. So now the scientists have, all the astronomers got together and said, you know what, we need to have one name for each one of these little babies, and then we all know what we're talking about. Constellations help organize the sky. So it's not just a stick figure connect the dots. It's just not those single stars or group of stars, but it's the region of space around it. And every star or galaxy is located within one of 88 constellations. So we have seasonal changes. As Earth revolves around the sun, the apparent locations of the constellations change from season to season. So we see a specific constellation here, and then later in the year we'll see it over here, and then we'll see it down here, and some of them we don't even see, okay, because they'll dip below the horizon. And now Mimiaga is going to stop with whatever he's playing with and pay attention. Some constellations can only be seen from the northern hemisphere and others from the southern hemisphere. And then later, as the year goes by, they switch. So if we can see it in spring and summer, then in the southern hemisphere, they can see it in the fall and winter. And what they see in the spring and summer, we see in the fall and winter. So there's really like 4 groups that we see based on the seasons. Finding stars in the night sky. You can use something called an astrolabe, and you can actually build this yourself. You can take I always get these confused, whether it's a compass or a protractor. You can use a protractor. That's the, it's flat on the bottom and round on the top. It's like dome kind of thing, and it's got the different degrees for the angles. Oh, he says it's a compass. Okay, so see, I told you I get them wrong every time. I never get it right. But that one, you can turn it upside down so that it's rounded on the bottom. Tie a string to the 0 and hang a paper clip from the bottom. Then you go outside and you line up the flat side with whatever it is you're looking at. And then that string will tell you an angle. Okay? And so you're using different locating vectors, I guess is what you call it. So you have altitude, and that's the angle between the object and the horizon. Okay? So that's what you get with the astrolabe. You're getting that angle. How far is it from 0 up or down? Horizon, that's where the sky and the earth look like they connect. And then zenith. That's the point directly above your head. Zenith. Directly above your head. And you've got a nice little picture here to show. Here's you. And here's the horizon that you see. And here's the zenith straight up above your head, 90-degree angle. And the altitude is the angle off of horizon. Okay? Again, Mr. Martin and I talked about this a couple of times. He may teach you the math concepts, but science is applied math. Okay? You don't really use the math in math class. You use it in science class. just like your language arts, you use in social studies. This is a really poor drawing of something that you have in your textbook. You actually have this picture in your textbook, the celestial sphere, because this is another way of finding the exact location of an object. The celestial equator is an imaginary line, okay, because we know that the equator is an imaginary line. Okay, so all we do is we take the equator and we just stretch it out. And that is the celestial equator. Okay, we've got the axis right there. The ecliptic path is here. Astronomers measure right ascension in hours east of the vernal equinox. And declination. So when you look at a map, like in social studies, you were taught to use longitude and latitude. Okay, longitude is where it is this way, and latitude is where it is on the globe this way. This is the same kind of thing, but bigger. It's, you know, the whole universe kind of thing. So they're saying from here, it's this many degrees to the east, and it's this many degrees north or south. Okay? Patterns across the sky. The path of stars across the sky. The apparent movement of the stars and the sun across the sky are because of Earth's movement. Okay? So, the stars aren't moving. Well, at least they are, but not so much that you can see. The stars are actually just hanging out, and we are moving. Now, there's something called circumpolar stars. Circumpolar stars. Circumpolar stars. These are the stars that you can see no matter what time of year, all night long. They're like circling around the North Pole. Okay? For instance, you've got the North Star, right there, and you've got these certain zodiac or other constellations that go around and around that one little star. It takes 24 hours for the stars to make a complete turn, because it takes 24 hours for the Earth to go around. So you can tell how many hours have gone by based on how far that particular constellation has gone around the North Star. So if it takes 24 hours and it started, okay, here's the North Star, and it's you noticed the constellation here, and then you fell asleep, and now it's over here. How many hours did you sleep? 12, because that's halfway. Right? So, because it's 24 hours all the way around. So you can use that to kind of tell how long time has passed. You can't really tell what time it is, because, you know, they're stars. Now, the size and scale of the universe. Objects farther away do not appear to move. Okay, and that's true if you're sitting in a car. If you're sitting in your car and your parents are driving along, the trees that you see right outside your window, they're going zoom, 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 zoom really fast. But the trees that are way out there, they aren't really moving at all. And so Copernicus used that principle and said, you know what? It must be that the planets are closer to Earth than the stars are, because the planets move faster than the stars. Ooh, science. It's amazing. Now, measuring distance in space. A light year. A light year is a unit of length that's equal to the distance that light travels in a year. Okay? So that's approximately 946 Hundreds, thousands, millions, billions, trillions, 946 trillion miles, kilometers. Okay? So, in math class, your teacher would say, please put that into scientific notation. So that would be 9.46 times 10 to the 14th power kilometers. Okay? Applied mathematics, people. Now, stars appear small, but stars are actually way more huge than the Earth. Very difficult to adequately comprehend these distances. I mean, our brains really don't think this way. But there is a table in your book, or an illustration in your book. It's on page 19, figure 7. And so they're showing you, like, here's home plate, and then here's this many miles away, and this many miles, and keeps taking you out further and further. So it's trying to give you an idea of just how big a light year is. But it's still, for some people, really impossible to just wrap their head around it. Now, if anybody ever watched The Big Bang Theory, the first party of pennies that Sheldon and Leonard and Howard and Raj went to, Sheldon dressed as the Doppler effect. Really confused everybody because he looked like just a big, tall, skinny zebra. Okay, and that's what everybody's like, you're a zebra? And he's like, no, let me give you a hint. Meow. Meow. Okay? That really didn't help people. Okay? So the Doppler effect, if you listen to an ambulance, when it's coming towards you, it sounds like woo, woo, and then once it gets to you and starts leaving, woo, woo, it changes pitch. That's called the Doppler effect. Okay? It didn't really change, but it's how we perceive it. Light works the same way. Light works the same way. So, if a star or a galaxy is moving away, the light that we see from that star or galaxy looks red. And if it's moving towards you, then the light we see appears blue. And we call that red shift and blue shift. Now, why in the world is this important? Who cares? That's like big deal. It's red or blue, big whoop. Well, let me tell you. Edwin Hubble, the guy who said, we are not alone, that there are many universes out there, he was able to use this Doppler effect, this red shift, blue shift, to prove that not only are there galaxies out there, but our galaxy is expanding. They're all moving away from us. They're probably scared of my students, and they want to get away. Just kidding. Alright, so after discovering that the universe is made up of galaxies, Hubble looked at that and said, dude, other than the galaxies that are closest to us, everybody else is moving away. It's red shift, red shift, red shift. Okay? So therefore, our universe is getting bigger and bigger and bigger and bigger. We're expanding. We're moving farther and farther away from each other. How sad that we're moving so far away from each other. Okay, and that, my little children, is the end of 1.3. So please, go to Jupiter and complete the section review, which is just called J 1.3 on Jupiter, but it's the section review questions from your book. Okay, and I will put 2.1 online. Thanks, Blas. So please, like and subscribe to my Facebook page, and return to me with joy and honor.